Hello everyone, I'm Mighty, your hands-on practice assistant. In this session, we'll go through a CFD simulation together step by step and follow along with the practice example. Today's practice example is Porous Media Flow Analysis. In this tutorial, we will learn how to analyze the flow characteristics of a fluid passing through a porous media. But first, what is a porous media? A porous media is a permeable material that allows fluid to flow through interconnected pores while creating pressure loss. Then, what is porous media flow analysis? Porous media flow analysis is the simulation of fluid flow through permeable materials to predict pressure drop, velocity distribution, and flow resistance. Before we begin the practice example, let's briefly understand the theory behind porous media flow analysis. Porous media are materials that contain many small interconnected pores, allowing fluid to pass through while creating resistance to the flow. Typical examples include packed beds, ceramic foams, filters, tube banks, and metallic substrates. In CFD, modeling every tiny pore requires an extremely fine mesh and a significant amount of computational time. Instead, we can replace the detailed geometry with a porous media model that predicts the same pressure loss using permeability and inertial resistance coefficients. For low-velocity flow, the pressure loss is described by Darcy's law. As the flow velocity increases, the Folkhammer term is added to account for inertial effects. Porous media models can also include heat transfer by considering properties such as porosity and effective thermal conductivity. Using this approach, engineers can efficiently predict pressure drop, flow distribution, and temperature distribution in complex systems without modeling every microscopic pore. Before we begin the practice, let's briefly summarize what we will cover today. First, let's take a quick look at the analysis model and boundary conditions. The model consists of an airflow domain and a porous media domain. The analysis conditions for each domain are shown on the screen. First, launch NFX and click Open in the upper left corner to create a new project. Next, go to the Geometry tab, click Import, and load the CAD model. Once the model has been loaded, right-click in the workspace and select Hide All Guides to clear the view. Now, let's create the materials and properties. When performing a CFD analysis, be sure to select the fluid and solid materials labeled for CFD analysis. First, create the air material. Next, click 3D, move to the 3D CFD Analysis tab, and create the property for the material you just defined. As shown on the screen, the airflow domain property can be created directly. However, the porous media property must be defined separately. Enable porous media, click Detailed Definition, and enter the viscous resistance and inertial resistance values as shown on the screen. Then, shall we generate the 3D mesh? First, let's review the mesh generation strategy for each region. Next, generate the 3D mesh as shown on the screen. Configure the mesh size settings and activate the checkboxes. After selecting all target regions for mesh generation, make sure that the properties have been correctly assigned. Then, click the arrow on the right and enable geometry proximity and avoid tetra with all boundary nodes to create a higher quality mesh. Set the mesh size to 0.002 meters for the porous media region and 0.005 meters for the remaining flow domain. When generating the mesh, make sure to activate the Match Adjacent Faces and Merge Nodes checkboxes. These options are required to calculate fluid flow and heat transfer properly between each region, so please pay close attention to this step. For the initial mesh generation, it is not necessary to enable the Match Adjacent Face Mesh and Merge Nodes options. However, for all subsequent mesh generations, these two options must be enabled. Now that mesh generation is complete, let's move on to setting the boundary conditions as shown on the screen. Follow along with the boundary condition setup process while watching the screen. Please also check whether the number of selected faces matches what is shown on the screen as you proceed step by step. First, select the inlet face, enter a velocity of 22.6 meters per second, and click OK. Next, select the outlet face, confirm that the outlet pressure is set to 0 pascals, and click OK. Finally, select all remaining faces and apply the wall boundary condition. Be careful not to select the inlet face, outlet face, or the interface between the airflow domain and the porous media domain when assigning the wall boundary condition. Let's move on to creating and configuring the analysis case. If you right-click Analysis Case in the Analysis and Result tree on the left, you can see several predefined analysis types. From here, create a steady-state CFD, then click Edit. You will then see an analysis setup window like the one shown on the screen a moment ago. In the General tab, you can specify the analysis module and iteration options. For this example, we will keep all settings at their default values. Before running the simulation, save the NFX file to your preferred location. Then, right-click the analysis case you created and select Solve to start the simulation. This analysis may take some time to complete, so we will skip ahead and review the results. In the analysis and result tree on the left, you can review the results for each calculated step. Click the desired result item to activate the contour display. You can also visualize the flow behavior using the flow path function to generate streamlines. You can also view vector plots by disabling the contour display in the upper left corner of the Results tab and selecting Slice Plane Vector in Vector tab. Now, let's review the analysis results obtained from the simulation. As shown in the results, the incoming high-speed airflow slows down significantly as it passes through the porous media. At the same time, the pressure increases upstream of the porous region due to the flow resistance introduced by the porous material. This demonstrates how porous media effectively models pressure loss and flow resistance without explicitly resolving the detailed internal pore geometry. While following along with today's practice, please make sure to remember these key points. How was today's lecture? Simulation may seem difficult at first, but if you follow the steps and practice hands-on, you can get started with confidence. With MIDAS NFX, learn the fundamentals one step at a time and challenge yourself with a variety of simulation examples. Then, see you again in the next video. This has been Mighty, your hands-on practice assistant.